Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of CERDUP and ESCCP. I have the pleasure of facilitating today's event. This webinar focuses on DoD-funded research efforts to develop technologies for PFAS removal and destruction. First, Dr. Chris Salas from Drexel University will present his work on the viability of using non-equilibrium gliding arc plasma to remove PFAS in water and solid matrices. Second, Dr. Stephen Richardson from GSI Environmental will talk about his research on enhancing the delivery of granule activated carbon for the in-situ retention of PFAS in subsurface environments. Each presentation will be followed by a brief Q&A session, and depending on how we're doing with time, we will conclude the webinar with a longer Q&A session. The next two slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provide it to you in your webinar registration confirmation email. If you cannot download Zoom, you can view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you have difficulty viewing the slides or if your screen freezes, try keying in Control and F5 to perform a hard refresh of your screen. And in case of continued difficulties, you can download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your confirmation email. Another option to view today's proceeding is to go to the CERDUP and ESCCP YouTube channel, as we will be live streaming the webinar. Today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A periods to submit your questions. We do encourage you to get them in well ahead of the Q&A sessions. And we ask that when you submit your question to add your organization name at the end of your question so that we can identify you during the Q&A sessions. Please use the chat box for comments related to technical difficulties. Do not submit questions in the chat box. With that, I would like to go ahead and introduce Dr. Cameron King, who is an ORISE Fellow with CERDUP and ESCCP. And prior to joining the program, Cameron worked in private industry with the DOE, EPA, and in laboratories at Old Dominion University, the University of Botswana, and the National Renewable Energy Lab. Her work has focused on thermal and biological conversion of organic waste, renewable energy, solid waste management, food waste reduction, and PFAS mitigation. Cameron received a bachelor's degree in chemistry and environmental science and policy from the College of William and Mary, a master's degree in geography and environmental engineering from Johns Hopkins University, and a doctoral degree in environmental engineering from Old Dominion University. Cameron, please get us started.
Thank you, Rula, and hello. I'm so happy to welcome everyone to today's CERDUP and ESCCP webinar. Thank you so much for attending today. I'm going to give you a little overview about CERDUP and ESCCP before the technical presentations. So CERDUP and ESCCP are companion programs. CERDUP is more traditional research and development program. It can be seen as the body of knowledge. CERDUP is actually a partnership between Department of Defense, Department of Energy, and also the Environmental Protection Agency. The CERDUP Council is made up of senior leadership from these organizations. ESCCP is demonstration and validation program. In many cases, we see research and development from CERDUP transition to ESCCP for demonstration and validation in the field. So there are 8 different focus areas within CERDUP and ESCCP, and these investments improve installation energy resilience, environmental cleanup, research conservation, and sustainment and maintenance of defense assets. And today's presentations will focus on the realms of PFAS and AFFF, as you see in that first bullet. So we cover a wide range of topics that include issues such as underwater UXO and climate change impacts. And every year we get to highlight these awesome projects at the DoD Symposium. So as we previously mentioned, we cover a large range of topics across many institutions, whether that's academic, federal, and within the industry. This graphic highlights PFAS projects and PFAS efforts. This is actually an interactive graphic that can be accessed on the CERDIP and ESTCP website with information and reports from projects that have been funded over the years through the many different topics. So these are the upcoming webinars that we hold roughly every 2 weeks. Our webinar series highlights outstanding projects across all main focus areas. So the next environmental restoration webinar is on May 2nd, and will feature 2 of our projects on PFAS destructive technologies, and we hope to see you there. You can find additional information about upcoming webinars at this link. All webinars are archived on this site, just in case you missed them. We would appreciate if you could please take a moment to complete the survey that will pop up on your screen at the end of this webcast. And at this point, I would love to turn it back over to Rula to introduce today's speakers. Thank you so much again for joining us, and I truly hope you enjoy this webinar.
Thank you so much, Cameron. It is now my pleasure to introduce our first technical speaker today, Dr. Christopher Salas, who is an associate professor in the Civil, Architectural, and Environmental Engineering Department at Drexel. Chris's research focuses on environmental microbiology, environmental biotechnologies, and environmental remediation technologies. He serves as the director of the Applied Plasma Biology and Chemistry Labs at the C&J Nieheim Plasma Institute at Drexel, where he leads efforts on the research and development of innovative, non-thermal plasma technologies for agriculture, food safety, public health, medicine, and environmental application. Chris received a bachelor's degree, actually he received bachelor's degrees in both chemical and biomolecular engineering and environmental studies from the University of Pennsylvania. And he also received master's and doctoral degrees in civil and environmental engineering from the University of California at Berkeley. Chris, please proceed.
Thank you, Rula. So for my talk today, I'll first go over and introduce non-equilibrium plasmas, and then I'll talk about the 2 gliding arc plasmatron systems that we're working on to destroy PFAS in liquids and solid matrices. And then we'll go over our studies and research looking into the mechanisms closing the fluorine mass balance and energy cost related to using gliding arc plasma in our project ER181570. And then I'll go over and compare GAP, the gliding arc plasma, to other plasma technologies and other emerging destruction technologies. And then finally, I'll go over the conclusions or takeaways from this webinar, as well as benefits to DoD of our project. So first, I'd like to go over the difference between thermal and non-thermal plasmas. So plasmas are ionized gases, and thermal plasmas are when the electron temperature and the gas temperature are in thermodynamic equilibrium. And what I'll be talking about today primarily are non-thermal plasmas or non-equilibrium plasmas. They're sometimes called cold plasmas, but they can also be warm, so above room temperature as well. So on the bottom, there's images of plasma arc welding, which is a type of thermal plasma, and dielectric barrier discharges, which you can see the person touching discharge are more at room temperature, at least for the temperature of the gas. So there's a few different types of flavors of non-equilibrium plasmas. There are corona discharges, plasma debts, dielectric barrier discharge, spark discharges, and gliding arc discharges. And I'll be talking more about gliding arc discharges in this webinar. So if you look into the literature, people have heard about plasma and plasma being used to degrade PFAS. Since about 2014, there are almost 30 publications on plasma treatment of PFAS. There's only one that has looked at plasma in degrading PFAS, specifically PFOA, in soils. And all of their studies are focused on treatment of PFAS in liquid solutions. And across these different types of papers, there's different types of reactors that are used. And one big question I often get is, how do you actually compare different plasma reactors? Are they really different? And they can be different. And sometimes when you look at these papers and hear about these plasma technologies, some key questions to ask when assessing these plasma systems are, what type of discharge is being used? What type of plasma gas is being used? And then how is that plasma being delivered to the material matrix? Is it from the top of the liquid or submerged within the liquid? And then what's the overall reactor design and how could that affect reactor efficiency and treatment? So these are very important to ask to determine the mechanisms of treatment, as well as treatment performance and energy, as well as impacts on their ability to be scaled to larger sizes. So Startup in ESTCP funds a few projects, a handful of projects using plasma. And I won't go through everything in this table, but each university or institution that has a project that uses plasma uses slightly different types of discharges or plasma regimes with their technology. So for instance, there's a DMAX plasma technology that Clarkson and the small business DMAX use. Clarkson also has a project using a plasma spinning disk reactor for treating AFFF solutions. And then out of the University of Idaho, they have a project using continuous flow liquid phase plasma discharge. And then at Drexel University, we actually use gliding arc plasmas or gliding arc plasmatron reactors for both treating liquids as well as solids. And we use primarily air, but we also incorporate looking at other gases as well used in these gliding arc plasmatrons. So right now I'm going to go over the systems that we have at our laboratory in Camden, New Jersey, at the Nieheim Plasma Institute at Drexel. And so this is our GAP liquid treatment system. We currently have two capacities, volume capacities, types of reactors where we use gliding arc plasma. One is a 1 liter capacity reactor, which has an electrode of about 100 to 1,000 watts. That's its power capacity. And then we have a larger scaled reactor that's 80 liters. It can go up to 3 kilowatts. We also have a solids treatment reactor, which we have called the Plasma Enhanced Thermolytic Reactor. And this reactor can treat solids. And the way that this reactor works is kind of like a fluidized bed reactor. So the plasmatron uses plasma gas, and the flow rate of that gas is upwards of 40 to 50 liters per minute. And this causes fluidization of the solids within that reactor. And so you can see on the images on the right, the fluidization of here sand within this reactor. And so this reactor here can treat about 1 kilograms of solids within the system. So now I'm going to go over the mechanisms, some of the research that we've done specifically now for the liquid treatment system. So for plasma, when there's a plasma discharge, there's multiple reactive mechanisms that can be involved in the degradation of PFAS in this system. And so we think and hypothesize that it's a combination of plasma-generated reactive oxygen and nitrogen species, specifically hydroxyl radicals for reactive oxygen-nitrogen species, hydrated electrons, as well as heat. So we've done some studies, and we recently published a paper last year looking at thermodynamic modeling of PFOA mineralization and comparing it to some experimental data from our GAP liquid system. And what we find out from this paper is that obviously the thermodynamics, the enthalpy of reaction is negative, so it requires some energy to actually degrade PFOA. And so it requires enthalpy input into the system or heat input. But we find out that with plasma reactive species, we can actually lower the temperature needed to achieve mineralization of PFAS. And here's some experimental data of showing that thermal degradation in this warm plasma, the gliding arc plasma discharge, is needed. So on the graph on the left, in the legend, you can see that there's increasing temperatures from 100 degrees Celsius to 630 degrees Celsius. So as we increase the power input into the reactor, we see that the defluorination increases. So the slope of that line, the percent defluorination versus time, that slope increases with higher temperatures or more power input. And then also another evidence of thermal degradation happening in this reactor is that we see near complete fluorine mass balance when we look at degradation over time within the reactor. So what that means is when PFAS is degraded, in this case PFAS, that almost all of it is turned into fluoride that we can measure in the system. We do measure some smaller chain PFAS, but they're at less than 0.1%. When we measure it in the liquid phase. And so we're able to come to a near complete F mass balance. Now we're also carrying out some other mechanistic studies. And in this case, we're also using argon in addition to air. And just a note about air. So the plasma gas chemistry for air includes reactive oxygen species from oxygen, and then reactive nitrogen species also from oxygen and nitrogen, as well as electrons in the gas phase. And when we use argon, the gas phase typically contains only electrons. But those electrons, when they reach water, they'll carry out the reactions that are shown on the right. But in short, they can generate both hydrated electrons as well as hydroxyl radicals in the water. So those are also reactive oxygen species when you do use argon as well, in addition to those hydrated electrons. And so in this graph on the left, we're comparing in the circles, the data points in circles to the ones in squares. The ones in circles are argon for both PFOA and PFAS. And we do see on this graph that's comparing percent of fluorination graphed against specific energy input, that for argon, it's more energy efficient. So the slope is steeper on that percent of fluorination versus specific energy. For argon versus air. And so this means that argon is more energy efficient than the air in our gap liquid treatment system. But even though that's the case, the plasma gas temperatures for argon actually in our system are about 150 to 260 degrees Celsius. So we hypothesize that heat could potentially also be important when using argon as a plasma gas. And so mechanistically, why is argon more energy efficient than air? Well, the goal in plasma is to strip electrons from those gas molecules. And so we're putting in energy, putting in electricity, and a lot of that electricity for air, these molecular gases, tends to cause vibration, rotation, and translational motion, which increases the temperature and also makes it harder to ionize those gases. So the argon is usually more energy efficient than air or these molecular gases. Now for these mechanistic studies, we're also investigating if hydrated electrons, so we do presume even in air that there could potentially be some hydrated electrons, and it's presumed that there's more hydrated electrons when using argon. So we've done some studies using sodium nitrate and sodium sulfite as hydrated electron scavengers. And on the graph on the left, using air, we see that addition of sodium nitrate doesn't cause any change in the percent of fluorination. So it has negligible effect on the fluorination kinetics. So it kind of tells us that hydrated electrons might not be important, at least under air, for defluorination. However, when we apply those hydrated electron scavengers with argon, that addition, at least above 1 millimolar, so 10 millimolar, 100 millimolar of nitrate or sodium sulfite, that we actually see that the fluorination, the ability to defluorinate the PFAS compound is enhanced with the addition of specifically sodium nitrate. So this might hint at the potential role of reactive nitrogen species in enhancing degradation, which was kind of an interesting finding that we found in our experiments. And so there's actually other papers out there that have shown that reactive nitrogen species could play a role in degrading PFAS. So there's actually some UV sulfite systems that have added nitrate, as well as some other DBD plasmids that also use air. And they've hypothesized that the enhanced degradation that they're seeing of PFAS is due to the formation of reactive nitrogen species. Then we look at the energy costs for this GAP liquid treatment systems compared to other emerging destructive technologies. We sit kind of in the middle of the road as far as EEO, the electrical energy needed to degrade an order of PFAS. And so here I'm showing on the left some calculations that we've done for argon as well as for air. And so like I said before, our air costs more energy, almost twice as much more energy as argon on the EEO scale. So it kind of falls in the middle of all these different destructive technologies. Now, transitioning from the liquid treatment system to the solids treatment system, we're still using the gliding arc plasmatron. And for this system, since we have solids in the reactor, our hypothesized mechanism, there's no liquid, there's no interface, but we do think that there's 3 potential mechanisms. So for plasma, there could be visual or UV that's emitted from the discharge. There could also be heat, as well as reactive species, those reactive nitrogen species or oxygen species if you're using air or oxygen, as well as ions, gas ions, and electrons. So we've done some experiments in our PETR system, our GAP solids treatment system, to look at PFAS removal. And what we find is that it's very temperature dependent. So like I said, unlike cold plasmas, GAP is a warm plasma discharge. So the more power we put into the system, the higher the temperature. And this is kind of showed in the graph below that shows time versus temperature. And you can see for at 480 watts, that we can only reach up to about 150 degrees Celsius. But if we bump up the power input to 660 watts, we can reach over time about 450 degrees Celsius within the reactor. And if we actually compare removal of PFAS that we've spiked, in this case on sand, and so we spiked 6 different types of PFAS, the carboxylates, sulfonates, and 1,4-toner sulfonate, we see that with the lower power and the lower temperature, we don't get much removal of any of the PFAS. But as we pick up the temperature and we increase the power input, we do see upwards of 99 to 99.9% removal of that PFAS on that solid. And we can actually do some experiments with other types of gases. So before we talked about argon in the liquid treatment system, and that's shown by the red lines here. On the graph on the right, you can see when we use argon that we can't really reach temperatures above 150 degrees Celsius. But for air, especially when we input more than 600 watts, that we can get temperatures upwards of 350 to 450 degrees Celsius. And it's the same case with nitrogen with higher power inputs. So we see that the lack of PFAS degradation at low plasma power and the good mass removal confirms that there's thermolysis, that you need temperatures to actually degrade or remove PFAS from the solids in this treatment system. Since we knew that temperature is pretty important and we want to think of ways to reduce energy cost, we try to use what's termed as plasma-assisted combustion. So plasma-assisted combustion has been used to ignite and also keep combustion going more efficiently with lean gases. So we actually operated the reactor with a lean mixture of methane. And we found, at least for removal of PFBA, to achieve greater than 95% mass removal of PFBA compared to nitrogen gas in the same system, that the overall cost, even if you include electricity and the cost of methane, is cheaper when you're doing the plasma-assisted combustion rather than just using nitrogen or potentially air in this reactor. Now we're working on trying to close the fluorine mass balance in this system. And so we've done some experiments using some impingers and some base traps to try to close the fluorine mass balance in this solids treatment system. And unfortunately, we're not able to completely close the fluorine mass balance. We don't see many PFAS compounds in the base traps. There's almost none or below detection limits. And there's not really much shorter PFAS observed in the base traps or the solids combined in the system. So we're still working on trying to close the fluorine mass balance on here and seeing whether we're removing the PFAS by thermal desorption and or by degradation. So from this webinar, hopefully what you've taken away is that gliding arc plasmatron discharges are warm discharges, and they're slightly different than cold plasma discharges like corona or BBD discharges that have also been used to degrade PFAS. So within these warm discharges, we not only produce plasma reactive species, such as reactive oxygen and nitrogen species and electrons, but we're also producing heat, which are really important in destruction of PFAS using gliding arc plasmatron discharges. We've also shown that plasma-assisted combustion using lean fuels could potentially be cheaper than incineration for treatment of solids, but there's definitely more work that needs to be done to understand the mechanism in both the liquid and solid treatment systems, as well as close the fluorine mass balance so that we're ensuring that we're completely mineralizing and destroying the PFAS, and there's no hazardous byproducts that are being formed either in the liquid or the gas phase from these systems. And finally, for our project, which has about a year left, we're hoping that by the end of it, we will be successfully demonstrating that you can use gliding arc plasma as a non-equilibrium warm plasma discharge to treat PFAS liquids as well as solids. And compared to other plasma technologies, we believe that gliding arc plasma is way more scalable to larger scales, being able to put more power per electrode in a design. And then from this project, we'll also be able to have an improved understanding of the degradation mechanisms and potentially energy costs using gliding arc plasmatron to degrade PFAS. And then from that information, hopefully we can have and provide preliminary estimates on the CapEx and OpEx to scale up this technology for full scale implementation. So that's the end of my talk. And so I'll be happy to take questions.
Great. Thank you so much, Chris. Just a reminder to please get your questions in using the Q&A function in Zoom. We did receive a number of questions for you. The first one is from the U.S. Army Corps of Engineers, Chris. And the question is, have you done any experiments with field contaminated soils or spiked soils?
Yes, for our seed project, which came before this full project, we did work with some contaminated soils from the Willow Grove Joint Reserve Base Naval Air Station, as well as some contaminated liquids from that site. And we are looking to obtain some more solids and liquids that are actually from the field to carry out more experiments, since we've done and gotten more experience with using these two different systems.
Great, thank you. This next question is from the University of Colorado, Denver. Can you elaborate on the mass balance issue? The inputs are PFAS, argon, and energy. What are the outputs after degradation? And do you have any concerns that that the byproducts may be hazardous, if at all?
Yeah, so we've used both argon and air as plasma gases. And for air, you do produce in the liquid some nitrates. And so that could be a potential concern in the liquid, and that might have to be dealt with after treatment. And fortunately, when we've done, at least in the liquid systems, the fluorine mass balance, it seems like we're getting very close, up to 99% of closing the fluorine mass balance. So whatever PFAS is degraded shows up as fluoride in solution. Now, the solid treatment system is a little bit more problematic. We haven't been able to fully close that mass balance. We're very far from it. We're only up to about 20%. So we have to do more work to figure out what other potential products, maybe gaseous byproducts or products that might be sticking to the system that we're not able to measure using our current sampling and analysis methods.
Great, thank you. This next question is from EPA. Have you measured the gas phase to look for PFAS that may be present at the temperatures that you are using?
Yes, we haven't measured in the gas phase directly. So we haven't done any gas sampling per se, but I think we're investigating finding collaborators. If there's any collaborators, feel free to reach out to me to do gaseous analysis from our solids liquids solids treatment system. And there's also potential, because we're bubbling so much gas in the liquid system, that there could be some volatilization or even aerosolization of PFAS that might be escaping the system.
Great, thank you. This next question is from the Connecticut Agricultural Experiment Station. Is it possible that one of the reasons that you didn't close the mass balance, the fluorine mass balance, is that HF reacts with the silicate minerals? Have you looked into that?
We have considered that, and we haven't perfected the methods to see if that pathway, if we're losing fluorine in that manner. So we definitely are kind of aware, and we're still investigating on developing methods for that. But thank you for the suggestion and further confirmation that other people are thinking of that could be a potential pathway.
Great, thank you. This next question is from ExxonMobil. What would you say your technology is better for, solids or liquids? Given the progress you've made so far, do you have a recommendation?
There are two different types of reactors. There's definitely positives and negatives. For instance, for the solids treatment system, especially in the current design, it's based on fluidization of the solids. And if you have a lot of clay and a lot of fines, with the high temperatures and the high gas flow rates, you're going to dry those fines, and it could be a very messy type of system to treat those solids. So those are some considerations for some drawbacks for that treatment system. And then for the liquid treatment system, it's very, that's going to have same challenges or some similar challenges to some of the other liquid treatment systems. I think for a lot of these destructive technologies, they both require a fair amount of electricity. And then that's one of our goals, is to try to reduce the amount of energy, electrical energy required for treatment of PFAS in these systems.
Great, thank you. This next question is from Boeing. For your energy efficiency calculations for the argon plasma, did you consider adding in the energy needed to produce the argon?
No, but that's a big question that we often get. I think a lot of the other plasma technologies use argon. We tend to favor the use of compressed air because of the limited supply, potential limited supply of argon, and it's slightly more expensive than air. So on our comparison of energy costs between argon and air, argon is only about 2 times more energy efficient. But there's estimates out there, and they're just kind of rough estimates that we've gone from doing quick Google searches, that it could be almost 100 times to 1,000 times more expensive to use argon versus compressed air. But we haven't looked specifically on the energy cost to actually purify argon from air and incorporate it into our energy costs. That would be something that we should consider doing.
Great, thank you. This next question is from the Department of Energy. Given the exceptionally low regulatory limits proposed for PFAS, do you have any concerns about the drop-off in performance when dealing with very low or very high concentrations of PFAS with your technology?
Yes, that's always a concern. I think for a lot of these technologies that require electrical energy, there's always the option of concentrating and treating a higher concentration and removing a certain percentage, maybe 99.9% or some log removal of the PFAS in there to reduce energy costs. Surprisingly, with when we've done comparisons of treating at ppm, so milligram per liter level, compared to ppt, so nanogram per liter level, at least on an energy basis, we don't see that more energy is needed to degrade at those lower concentrations. But we only have a few data points showing that, so we definitely have to do more experiments to see if it's truly the same energy cost at the lower concentrations. But I think dealing with low concentrations and seeing if this technology works is a very important task to do.
Great, thank you. This next question is from an anonymous attendee. Have you done cost calculations to figure out what the cost to scale up your technology is, and have you compared your costs to other technology options for PFAS?
We haven't done a full cost calculation or estimation yet. That's definitely part of our task list for our current sort of project. So if you reach back to us next year around the same time, hopefully we'll have some results to share.
Great, thank you. Back to some specific questions that have come in. On slide 30, you mentioned that you're fully destroying the PFAS, but defluorination is roughly around 50%. Is that because you don't show the full experiment? What is the reason for the 50% defluorination, but your statement saying it's fully destroyed?
Yeah, so I think what my comment is saying is those experiments that I showed only show kind of a truncated experiment. So what we're seeing is pretty linear energy input to defluorination as well as degradation. So when we run longer experiments, we achieve higher amounts of defluorination. So in those experiments, we're not receiving. But I think from my comment is because we closed the fluorine mass balance, basically any PFAS that's removed, we see the equimolar amount or equivalent amount as fluoride in solution in the liquid treatment system. So any PFAS that's degraded, and it might not be all of it, we see it show up as fluoride in the liquid.
Great. A question from the Air Force. What is the nature of the liquid samples? Are these IDW liquid samples, or is it clean water that you spiked with PFAS?
So everything that I showed today is clean water. We have run some experiments with groundwater, with diluted AFFF solutions, but I didn't show those in this presentation.
Chris, just as a follow-up, did you get the same type of performance in non-clear water matrices?
Yeah, so we don't suffer as much as some light-based or photochemical or indirect photochemical methods, because there's heat, there's reactive nitrogen species present. So that doesn't affect plasma as much. But when we did compare and look at degradation of groundwater, the rate is slower, probably because of other co-contaminants or other constituents in there.
Great, thank you. And then from Boeing, what do you do with the fluorine that is generated by the system?
That's a good question. I think in the laboratory, we're very careful because we have PFAS, so it's definitely being stored and we're making sure that we dispose of it correctly. But I think in actual practice, that's a good question. I haven't really thought about that.
All right, and two quick questions before we wrap up and turn the floor over to Steve. The first one is from an anonymous attendee. What dominates the destruction of PFAS in your system? Is it the temperature or the plasma? Have you looked into that?
So we haven't looked at the percentage. What we've seen is that temperature is required, or at least it's very beneficial in our system. But based on kind of activation energy barrier, we see that the electrons, the hydrated electrons or electrons in the gas phase, if there's reactions taking place at the interface, as well as the hydroxyl radicals, are lowering the amount of energy required to degrade PFAS and mineralize it. So it's a combination of both, but temperature is definitely something unique in our system compared to other cold plasma technologies.
Thank you. And this last question is from the University of Minnesota in Duluth. What can you share? What type of methods you plan to use when you investigate the closing the mass balance issue? What sort of methods? Non-targeted analysis? What are you looking at using as you continue your work?
Yeah, I'd probably defer this question to our collaborator, Erica McKenzie at Temple, who's also helping on this project. She has a QTOF where we can do some high-res mass spec to do non-target analysis. But we're also exploring like GCMS, and there's a TOF SIMS also from one of our colleagues in chemistry at Drexel University that has been used to measure gaseous PFAS as well. So we're going to consider trying using all those, but I'd be happy to receive any emails if you have any suggestions on other ways to close the mass balance, especially things that are released into the gas phase.
Great. Thank you so much, Chris, for doing a great job with both your presentation and the Q&A session. At this point, we're going to go ahead and transition to our second presentation, which will be given by Dr. Stephen Richardson. Steve is a Vice President and Principal Engineer at TSI Environmental in Texas. He serves as a PI and co-PI on a number of projects being funded by CERDUP, ESTCP, DOE, the Air Force Civil Engineer Center, the National Defense Center for Energy and Environment, and the Naval Facilities Engineering Systems Command. The topics of his R&D efforts include PFAS fate and transport, innovative technologies for PFAS treatment, amendment emplacement in low permeability zone, and the degradation of chlorinated solvents. Steve received a bachelor's degree from the University of Waterloo, a master's degree from Louisiana State University, and a doctoral degree from the University of North Carolina at Chapel Hill. Steve, please go ahead and get started.
All right. Thank you very much, Rula, and thanks to ESTCP for the opportunity to present. Good morning, everyone. Good afternoon, everyone. Really excited to discuss this technology that we've been working with for the last 5, 6, 7 years, and its application for the treatment of, in situ treatment of PFAS in groundwater. So we'll jump right in. So in terms of a presentation outline, we'll quickly go through a problem statement, talk about the technical objectives of this project, explain a little bit about the technology that we're testing out here. We have a field demonstration coming up this year, so we'll give a very general overview of what the plan is, some operational considerations associated with the technology, conclusions, and then benefits to the Department of Defense. So many of us are pretty familiar with this type of problem statement. Again, those that are familiar with groundwater plumes, we often, particularly with PFAS, we often see those to be pretty large dilute plumes, many of them a few ppb or less. But we do see source zones that can have much higher concentrations, in some cases hundreds of ppb, and then in some other cases even as high as single-digit ppm. So there are some really large variation in concentrations that we might see at a particular site. In terms of managing PFAS impacted groundwater, I think the messaging has been pretty consistent that it can be pretty costly. And primarily we focus on ex situ approaches, pump and treat being one of those. We have revitalized or brought back pump and treat at many sites just to deal with concerns with off-site releases or nearby receptors. And then disposal options are extremely costly as a result. So, and it can be impractical for really large volumes of water. And so, as an industry, we're looking for ways, as Chris had mentioned in the previous webinar, to either concentrate water and then looking at destructive approaches. But there are a variety of different tools in the toolbox, and I'm going to be sharing one of those today. So what we're looking for are these reliable in situ. So can we get away from an ex situ approach and start looking for something in situ, which obviously has some cost benefits that would soak up or retain PFAS and co-contaminant mass over time. So I've had the fortune of working with Keller North America and formerly Hayward Baker. And often it's interesting talking with folks from other industries, other environments, and to see the types of technologies that they have at their disposal. And the geotechnical industry is really good at accessing the subsurface. That is their specialty. And they have a variety of different technologies that they use to do exactly that. The grout bomber, which is the technology we're going to be discussing today, is one of them. But there's also a whole host of others. There's the wick drains, which is again used for consolidation of materials. Jet grouting, we do see some jet grouting in the environmental field. And then other deep vibration. Again, these technologies are really used to stabilize the subsurface, but the selling point is that they can be used to quickly and efficiently access the subsurface. And so that's what really got our eyebrows raised when it comes to these types of tools. The grout bomber is a soil stabilization technology, as I mentioned. Its goal is really to deliver cement grout into subsurface voids. And how I came into contact with the grout bomber was at a site that Keller was working at. It's a former landfill. They were intending to build on top of that landfill. And of course, there are voids within a landfill. And so the goal there was to basically go in, inject cement grout into those voids, not only to fill those voids, but also squeeze the material in between those injection or emplacement points so that you are creating a stable foundation to build upon. It is a direct push technique, just like the techniques that we use in the environmental field to do either DPTs or to install our monitoring wells. And it's appropriate for silts and clays mainly. Again, materials that have fairly low blow counts, so things where they're a lot easier for a direct push technique to make its way through the subsurface. Specifically, that would be blow counts of less than 40. And then in terms of installs, this is one of the check marks, I guess you could say, when it comes to these types of technology, is that we can access the subsurface over 100 times per day. And these are at depths of, in my experience, 30, 40, 50 feet. You can achieve very close spacing of those holes, 2 to 3 feet. And then as a result, there can be some cost savings as well. On the right-hand side is a picture of the bomber. It's a 350 excavator with the mast. The mast is essentially the depth that you're intending to go. So in this case, was about 40 feet, 50 feet high if you're interested. And then at the bottom is exactly as it looks. That's the cement grout coming out the base of the mandrel, and it has a associated name that makes a ton of sense. So there you go. And then in terms of how the grout bomber operates, it's pretty simple. I mean, essentially there's an Elkin mixer that's involved. From the cement grout side of things, that would be aggregate, cement, water, additives. It's all mixed together. It is then moved to a hopper where there's amendment pumping, and it is delivered to the top of that mast through a series of hoses to the top of the mandrel of the bomber. But our application isn't to talk, the purpose of this talk is not to talk about cement grout, but in fact, can we actually replace that cement grout with something that's more applicable to the environmental field? And in this case, what we're talking about is delivering a sorbent material, granular activated carbon, but it could be another sorbent material as well. And so not cement grout, but instead repurposing the grout bomber technology to deliver sorbent material such as GAC. So technical objectives, again, we want to demonstrate that the grout bomber is one of the tools in the toolbox for addressing PFAS groundwater plumes. We plan to do that by creating a permeable sorbent barrier, so analogous to a permeable reactive barrier, but without the reactive component, obviously. And so this PSB will consist of hundreds of vertical columns. They'll be closely spaced in the neighborhood of 2 to 3 feet apart. And it really serves as an alternative method of sorbent delivery. Again, there are vendors out there and actually current techniques that we use to inject material into the subsurface. The goal here is that we're actually emplacing the material in these columns and creating them as closely spaced. In terms of GAC, the purpose again is to serve as a sponge to sorb the PFAS. we're focusing on GAC. Again, it's not the most ideal sorbent for PFAS. Again, better for longer chains, not as efficient for shorter chains, but it is relatively inexpensive compared to other injectable sorbents. And so our idea here is to put enough GAC in to kind of overcome some of those limitations. The other point is that we do recognize that if you put carbon in the subsurface or you use carbon to sorb PFAS or any compound for that matter, it is a reversible reaction or reversible sorption. So there is the possibility of desorption of this material off of the sorption sites on a granular activated carbon particle. So it is not at this point viewed as an end all be all technology that's going to solve all of our problems, but it certainly could be used as a potential interim remedy, where if you have a PFAS plume that may be moving off site, you could create this barrier along the boundaries of that site and prevent interaction with any nearby receptors. So that's our thought process at this point. In terms of the permeable sorbent barrier, how does it differ from our traditional amendment injections? Again, the traditional amendment injection may involve injection wells or DPT points where you're injecting in certain intervals. They tend to be further apart. It could range from anywhere from 10 to 30 feet apart. And then you end up injecting into those sort of higher K zones, really, and try to create connection of that amendment with the other location of your injection point. For the grout bomber, at least for this application, our goal is not to inject necessarily, it's really to emplace. So we're actually creating these granular activated carbon columns that are, and hundreds of them, that are really closely spaced. So again, it's not an injection technology per se in terms of the application, but rather that we're emplacing and creating these kind of GAC columns that are closely spaced together. So that's kind of the thought process, but all of this relies, again, because we are creating, essentially those columns don't touch. So it is a discontinuous permeable sorbent barrier, and the idea is, well, how is that going to work? Well, it relies on a phenomenon called the lens effect. And so again, this is a critical part of this study, is that, again, the lens effect is basically a hydraulic conductivity difference between the GAC that is in that column and the native material. And so this has been done. These are unpumped. This is a phenomenon that USGS had mentioned this about 20 years ago now, an unpumped well, where essentially you can draw local groundwater flow lines towards those columns because of that difference that exists between the media that's in the column versus what's in the native soil. If you do some calculations, you can end up figuring out that the PSB with 10 times higher K than the aquifer, you can achieve a capture zone of about 2 times the well diameter. And so the mandrel itself that we're creating is about 3.5 inches in diameter. So now you're looking at sort of a 10-inch area. So there is some obviously that doesn't close that gap, but what will improve that is by staggering those transects. And so you can see in the bottom right picture, what we end up planning to do here is staggering those rows and making the column, the PSB, fairly thick, so that there is going to be some connection between the groundwater flow lines as they're flowing towards that PSB is actually interacting with those granular activated carbon columns. Where we are in the project, we've finished site selection. We'll talk a little bit about the site in a second. We've done some very preliminary groundwater modeling. We're in the middle of amendment selection right now. And then, as I mentioned, we'll have a field demonstration at NES Jacksonville towards the end of the year. So we're moving towards that. We're doing the work that's necessary to kind of prep for that type of activity. The site that we're focused on is the Petroleum Contaminated Area 15 at NES Jacksonville, past fire training area activities for certain. And PFAS concentrations pretty high, hundreds of ppb, and in the source area up into the ppm range. There are some hydrocarbon impacts as well. Benefits of the site is that there's an existing monitoring well network. We have lots of historical PFAS data. And then another plus that not only just applies at Jacksonville, but also at other fire training areas is that there's tons of space. And so this is not a small piece of equipment. It really does allow, we do need some space to move it around and position it as it swings around and installs a column. It will move 2 feet and install another one. And so it's going to need some space to move around. And the benefit of fire training areas is typically there's room to do exactly that. In terms of the geology, it is a little complicated. We have, the aquifer does have a couple of zones. One is the shallow zone and the intermediate zone. So if you look in the inset, we can move from the source area, which is where the fire training activities were occurring, and you move more towards the northeast along that transect. You can see that where we put the purple curve, that's where our barrier is going to be. It's going to intercept the plume, at least in that area. That will also, if we're installing to about 30 feet deep, that'll include the shallow zone as well as the intermediate zones in terms of connection with the granular activated carbon. That column will be filled with carbon from top to bottom, so from the surface all the way down to depth. In terms of whether this was a good location for us, we have done some penetration testing, and we're able to show that, yes, we feel very confident that the bomber can push through this material, again, which consists of a mixture of sand, silt, and clays, but generally below counts that are less than 40, although there are some zones that get a little close to that might make us a little uncomfortable. But at the end of the day, in talking with our vendor and partner, we do feel pretty confident that we can achieve many accesses to the subsurface as possible. In terms of the PFAS distribution, if we look at another cross-section, this is HPT work that was done by, partially was done by Aptum, and appreciate their involvement. This is another ESTCP project that is working in the source area. There are actually 2 or 3 other projects, and I appreciate all of the members that have worked together to share information. But if we move ourselves from HPT01 all the way to MW03, we can get a sense for the concentrations that we're dealing with at the site. And the orange line, because I made the biggest mistake with not including a legend, but I can help walk you through that. The total PFAS is the orange line, and then the blue is PFOS, red is PFOA, and then the gray and brown are 6,2-FTS and PFBA. So we did some select analytes. So if you move yourself from left to right, the story is really that we see higher concentrations of PFAS at the deeper parts of the intermediate aquifer. And the concentrations are upwards in the hundreds of ppb, and as I mentioned, single-digit ppm. So very, very high concentrations that we're dealing with as you move from the source zone all the way down to the area where we'll be, which is, again, hundreds of ppb in terms of total PFAS. The design and optimization, it's going to be a 3-pronged approach to arrive at the final design. We've done some preliminary groundwater modeling, looking at various configurations. That would be how many rows of columns do we need? How closely spaced should those columns be? The amount of staggering that we do. So we've played around a little bit with that. Also looked at the potential effect of density artifacts. So if this is a direct push technology, we'll essentially be pushing down and squeezing some of the material around that emplacement point. And what is the effect of flow lines if you're squeezing some of the material around there? Amendment selection, we will look at commercial availability, obviously is a big one, pumpability, and then cost. And then last, we're going to do some isotherm testing and viscosity testing to evaluate the pumpability of the selected carbon product. So just a little bit on the modeling analysis, and again, this is very high level. We were, again, playing around with the number of columns, the spacing between the columns, the spacing between the individual emplacement points. And when we looked at all the scenarios, at the end of the day, we were able to achieve about PFAS mass removal about 95 to 96%. To gauge whether that's good, bad, or ugly, if you go into the literature and look at what colloidal activated carbon, the field experiments that have been out there, and there's a fair few that have been done with some of the commercial products. they're achieving anywhere from greater than 90 to greater than 99% PFAS removal at this point. Again, the biggest question, and I'm sure we'll talk a little bit about that in the question and answer, is longevity of these columns and potential for rebound. But at least in the literature that we've seen, the removal within the first 2, 3, 4 years ranges from 90% to 99%. And then looking at the density artifacts, we've done some basic modeling as well as some lab experiments, and basically reduced the capture by only about 0.1% over multiple model runs. And so that little image on the right-hand side shows that the flow lines before we go ahead and install, we make some sort of disturbance. This is what it would look like without the disturbance, and then of course after the install with the disturbance. And so we wanted to understand how much effect does that have on the actual flow of the system. In terms of amendment selection, the goal here is a balance. So the GIC mixture's got to meet the following criteria. It's got to be pumpable. We can't have material stuck in the hoses and so on. Mixture needs to be more permeable than the formation to achieve the lens effect. We want to have a high mass percentage of carbon. So we want to put as much carbon as we can in the ground. That's one of the goals here with this project. Carbon must stay in suspension during the pumping, and then obviously settle out within the column. And we're looking for obviously low material costs. So anytime we can use a granular activated carbon, we're probably going to find ourselves in that sort of low cost range. Preliminary findings, not surprisingly, we were trying to mix things and play around with different aspects. One was to play with sand just as a filler. But of course, sand tends to settle out. We've had some experience with the grout bomber before, and it didn't work out so well in terms of pumping. It becomes difficult to pump, and so we would like to stick with just GAC. We tried some PAC, so powder activated carbon. It works really well. It serves as an emulsifier, good for viscosity, but not so good for the permeability, at least at this site. So it's certainly a consideration for maybe other sites, but not for the one that we're looking at. So we're leaning mainly towards mainly a GAC, primarily GAC in those columns. We also are considering some other sorbents that are more PFAS specific. We may consider doing that as an offset to the column as well. Specifics of the column are that it's 250 feet in length. We're going to put 1,250 sorbent columns, 8 to 10 rows of staggered offset GAC columns. The depth will be to 30 feet. And the goal here is that we're going to install 75 to 100 of these columns per day. So it's pretty amazing what can be done in 10 to 15 field days with this technology. In terms of performance monitoring, we have a variety of methods that we're looking at. One is just obviously simple piezometers. We're going to put those up gradient and down gradient and around the side of the permeable sorbent barrier. Goal there is we want to make sure we clearly understand the flow field and confirm that we are in fact getting the lens effect occurring. We also have permanent monitoring wells going up gradient as well as down gradient. And then they will all be analyzed for PFAS, TOF, VOCs, and a whole host of water quality parameters. Obviously, I mentioned we want to evaluate that flow field pretty carefully. We want to look for areas where there may be some potential bypassing. One of the cool things about the bomber that I always like to highlight is that it can also be used to install other things. And one of those things is a CMT well. And so for those who may not be familiar with a CMT well, those are different. It's a well that's sort of all encompassing in this tube. So you have different intervals that each tube is set to a different interval. And so it's all in one place. And the benefit of the bomber is that you can actually use bottom feeding as a way to install a CMT. And that would allow us to put a CMT right in the center of a granular activated carbon column. And you might ask yourself, well, why in the world would we want to do that? Well, it allows us to actually sample water from the pore space within one of those columns and make some determinations as to whether we're seeing absorption occurring, are we seeing any change in concentration, and so on. And so it's simple as pushing the CMT up the mandrel, the grout bomber pushes down to the base of the location, and then as you pull back up, you're filling that annulus with your granular activated carbon and then moving to the next location. So the biggest question is, will it work? The answer, that was the toughest question in some of these research projects. But we do have some information to rely on. We have done another ESTCP with the bomber, and this focused on treating low permeability contaminated material in a CVOC source zone. And so we actually pumped a combination of ZVI, zero valent iron, sand, and vegetable oil into a source area at a site that was up in Maryland. And the operational results were really promising. We were able to put about 800 of these reaction columns in a very short period of time, 7 or 8 field working days. In some cases, over 100 columns per day with a maximum of 180. We went to a depth of about 30 feet. And then 77,000 pounds of ZVI were in place. And we are seeing, again, this is a diffusion-based application, but we are seeing degradation of TCE and production of those daughter products over time. I'll finish up. I've got a couple more slides here, and I'll finish up with just some operational considerations. Again, that the bomber is a really interesting and useful tool, but it's not the answer to everything. And so there are some things we've got to take into consideration when we might select it as a technology to use at a site. One of those is that it requires vegetation clearance and a really, somewhat of a flat surface. And the good news is that fire training areas, that's usually not a big issue. It does require a full day for setup. It is a big piece of equipment. The blow count issue, as I've mentioned before, it's more ideal with those silts and clays. And you need a well-characterized site because we are creating hundreds of these vertical columns. So there's the potential for vertical contaminant migration. So you have to have a very good handle on what is happening hydrogeologically at the site. Bomber benefits are that we can hit some pretty deep depths, 50 plus feet. If you're talking about wick drains, for example, another similar technology, they can get up to 100 feet. Different amendments can be used, as I've mentioned. And then the other consideration here on the bomber is that we are filling from surface all the way down to depth. So you can't, at this point, target the amendment for a certain zone. I guess we could do some variation, but if we're using this technology off the shelf as it is, we have no way to do that at this point. And the mobilization cost can be pretty high, but that is counteracted by obviously the volume or the rate at which it can access the subsurface. So you have more holes to put in or a larger area to deal with, that cost becomes less and less of a consideration. And then conclusions, again, it's a promising technology. It can rapidly install these sorbent columns for a PSB. It's certainly an alternative method for sorbent delivery, one that can put environmental practitioners as another tool in the toolbox. Expected performance is consistent with what we're seeing out in the field in terms of CAC work, although again, this will be the testing ground for that. We do estimate that we can deliver more carbon per unit volume than what we'd see in a typical colloidal carbon injection. And we've got some preliminary costs, again, $40 per cubic yard of treatment volume. That's within the zone of the PSB. But again, once we get that field demo done, we'll have a better sense of costs down the road. And then in terms of benefits to the DoD, we can deliver these large quantities of sorbents. We're hoping to see some cost savings relative to conventional injection, and obviously, most certainly, we want to avoid pump and treat. And then the alternative, it's an alternative to conventional injection systems for a heterogeneous site. So that's where we stand. I do want to acknowledge a few people, NAS Jacksonville folks, Mike Singletary, Chris, and Dave, for their help, our fellow ESTCP teams that are working with us. Appreciate all of their input, and then the project team that's listed here. And I left with a couple of additional resources for you guys to look at, something to keep you up at night if you enjoy reading these types of things. Some really good resources that talk about the bomber as well as some of the particulate carbon work that's being done out there. And then I'm happy to answer any questions at this point, and thanks again for the opportunity to speak with you.
Great, thank you so much, Steve. We have received 3 or 4 permutations of this first question that I'm going to relate to you. This version is from the Bureau of Reclamation. what do you do with the spent GAC? Do you leave it in ground, or do you dispose of it at the end of the project? However, you know, after the 4 years that achieve the 90% removal that you referenced?
Yeah, it's the $1 million question. So at this point, the answer is that you leave it in the ground. And that would be a similar question that you would ask for any particulate carbon amendment injection at this point. The simple answer is that what we would expect in terms of longevity, and I want to make sure that I'm clear, is that what we're seeing in the field demonstrations or field research at this point, it's certainly, we're seeing longevities of greater than 5 years. I wouldn't be surprised if we see longevities greater than 10 years or more. So that doesn't fully answer our question of something that is being an end goal treatment. The option is that you can go back and build another PSB. You can put another row of columns in. There are some discussions that we're having of potentially figuring out ways that we can pull the material out. And then there's some other technologies where they smolder the material, and we've been in discussions with to see if that might work for this. I'm not sure it will, but it's certainly something that we're considering. So we do recognize that this is absorption only technology and that there is not a destructive part. So it is really interim and really at this point can't be considered a final remedy.
Thank you so much. This next question has to do with the empty bed contact time. This is from an anonymous attendee. Do you know the estimated empty bed contact time in your permeable wall, and how would this compare to a continuous barrier?
Yeah, I don't have that number in front of me. And how would it continue? It would be the same as a continuous barrier in my mind, in some ways. The thickness of a continuous barrier is typically, especially if you use like a one trench technology, let's go with that, could be in the neighborhood of 3 or 4 feet thick. And if you add up all of the rows that we've got, we've simply broken that kind of apart into little bits. So I don't have the number for the empty bed contact time, but my assumption would be that it would be very similar to what you'd see for an existing permeable reactive barrier that might be put out there.
Thank you. This next question is from Noblest. Do you have information on how this technology compares with shallow soil mixing to deliver GAC or other amendments in terms of cost and performance? Have you run these numbers?
Yeah, so we have run the numbers, but it's still not an apples to apples comparison. So the site that I'd mentioned where we did the ZBI source zone, they actually did a soil mixing at another portion of the plume. Again, what we discovered here is that yes, the soil mixing, because you're adding that mechanical motion in and you're actually creating or forcing contact between the contaminant and your reactive amendment, you're going to see lower concentrations or more of a reaction than you would if we just created these columns. And so in that case, we were relying on diffusion to do the majority of the work and moving the contaminants towards the reaction zones. If you just mixed all those together, you would have the benefit of the mechanical energy that was put in and the contact between the two. My guess at this point is that it is operationally cheaper to obviously go and put in these individual columns, but the expectation would be that it would take much longer for your contaminants to be degraded. And I'm talking about chlorinated solvents in this case, than would be the case for a soil mixing setup.
Great, thank you. This next question is from Orange County Water District. For your proposed demo at NAX, can you confirm that you're going to only inject GAC mixed with water, or are you going to mix granule activated carbon with a powdered activated carbon or a CAC?
Yeah, we don't know the answer quite yet to that. There may be a little bit of pack we put in. We're still working through some of the lab experiments, looking at changes in viscosity and pumpability. But it will be majority GAC, mainly driven by the fact that there's a cost element here that we like to try and use the most cost efficient material that we can. We also want to maintain that permeability difference between the native material as well as the native material and the column material. So if we put too much pack in there, we start to get pretty close to what's in the aquifer, and we may not see those bending of groundwater flow lines like we'd like to see.
Thank you. This next question is from the Michigan Department of Environment, Great Lakes, and Energy. What do you expect to see in terms of migration of material from the placement location over time? Have you done any bench scale studies to look into that?
We have not done any bench scale studies for that. But I do expect there will be some movement of material in the aquifer. But the goal would be to keep the size, the particulate size. So that's why the PAC portion of this, we have to be very careful about the amount we put in, because it will find its way into the aquifer much easier than the GAC. We do want to stay as granular as we can for that particular reason. If we go back to the other site that I mentioned where we'd done the ESTCP work previously, the source zone, that was mainly clays and silts was the media there. And so there was a very big difference between the media and the column, the ZBI and the silts and the clays surrounding it. We have done some work there where we put soil borings within the column and just outside the column. And it's a very drastic difference. You don't see any of the ZBI moving outside of those columns. In this case, I would expect there will be some, but I don't expect there to be a lot of movement from those columns to, through the aquifer down gradient.
Thank you very much. This next question is from the Navy, and you've sort of addressed it a bit. It's about going back and doing multiple applications after you start seeing breakthrough. How would you do that? Would you add columns down gradient of where you originally emplaced them, or would you stagger them within the existing barrier?
You could do
what
both.
are you thinking?
Yeah, that's a great question. You could do both. You could look for areas where perhaps we got the flow, because again, the flow through a barrier can be complicated. You don't really know where groundwater is going to go, 100%. So you might find that one portion of the barrier is actually, you're seeing a lot more desorption or a lot more breakthrough of PFAS than in others. So you could focus on that area. I do think that you could install in between. There's no reason you couldn't. You'd also could install another row down gradient. You could install several rows down gradient. You could also build up gradient if you wanted to, but at the end of the day, you have the capability. The spacing of these rows will be such that you could come in and put additional columns in between. Great,
thank you so much. This next question is from EA Engineering. Have you considered the effect of alkaline conditions from the grout on PFAS mobility?
We have to some degree, but not fully looked at it. So it's possible, yes, there can be some issues with the variety of different PFAS that may be attached or not. But at the end of the day, we do expect that given the water at NAS Jacksonville, which is, I believe, slightly acidic, there's probably going to be some balancing act when it comes to pH. So I don't expect that we'll see a whole lot of impact by alkaline conditions, but at the end of the day, it's certainly a factor that we'll look at.
Great, thank you. This next question is from AECOM. For the added GAC, have you looked at adding any chemical additives or heating the mixture before injection to facilitate delivery?
Yes, we can. The goal here is to try to keep the technology kind of turnkey as best we can to see if we can use it sort of off the shelf. We can heat things up. We can change a few things. So we have talked about it, but I don't know if we'll actually go ahead and execute it. We may do that in a portion of the barrier, but I think by and large, what we're trying to do is just say, hey, can we get a boatload of carbon in the ground using the existing setup, make some variations where it makes sense, but at the end of the day, try to keep it true to the goal, which is to repurpose the technology.
Great, thank you. Any parting thoughts or messages that you'd like to make sure you leave our audience with today before we wrap up?
That's another $1 million question, Rula. I think that I will say just being part of this program and doing the type of work that we get to do and engaging with all these smart people. I know there's a lot of fear with PFAS and a lot of the thought that we're not going to be able to treat this stuff. But when you look at all the technologies that are available to us, there's a lot of hope and a lot of belief that we can actually achieve a lot of the goals that we set out to do. It's not like we don't have a toolbox on the remediation side to deal with this class of compounds. So I do feel very fortunate to be part of this program and excited to see all the other technologies that are coming out and making their way to the commercial side of things.
Great, thank you so much. I'd like to thank you both our speakers today for really great presentations and engaging Q&A sessions. Again, if you have additional questions, the contact information for both of our speakers is included in the PDF of the slides that you can download from the CERDUP ESCCP website, and there is a link in the chat box to those slides. At this point, I'd like to go ahead and wrap up and remind you that the next webinar in the CERDUP ESCCP webinar series is on Thursday, April 25, and it will feature research efforts on the use of advanced sonar-based deep learning for underwater unexploded ordnance remediation. You can visit the CERDUP and ESCCP webinar webpage to register for this and other webinars through the end of this year. The next ER webinar is going to be in a month on May 2nd, and the focus of that webinar will be on PFAS destructive technologies, so make sure to tune back in. And before we conclude, I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on the webinar webpage. We would appreciate it at this time if you can take a few moments to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you so much for